Okay, and then one last thing to cover for our particle in a box system is the energies that we end up with after solving our Schrodinger equation. So if we think back a couple of slides to where we had said that our Ka is equal to n pi. Okay, so remember that came from applying our boundary conditions. Okay, so you can look back if you forget where this expression came from. So that was our sign of Ka equals 0, and then we said Ka is integer numbers of pi, not including 0. Okay. Remember way back when we defined our K, we said that K is equal to 2me to the 1/2 over h bar. Okay, so we'll just plug that into that expression. So we would end up with 2me to the 1/2 over h bar times a equals n pi. All right, so far so good. And then remember our n's start at 1 here. Okay. All right, so now where are we going with this? Well, hopefully you can see that now we are able to solve for our end quantity that we were looking for, right? Remember solving the Schrodinger equation, the eigenvalues that we want to get out are the energies. Okay, so we're just going to solve for E here in our expression. Okay, so when you do that, you will end up with, so let's say we have, let's just square everything, make it easy on us. All right, so then we'll have E equals n squared pi squared h bar squared over, oops. Oh, no, that's okay. Over, I thought I forgot to square 2, but I did not, so we're good, over 2m over 2m. Okay, so there is our solution for the energy levels of a particle in a box in terms of h bar squared and n. And you will also see energy, I would say probably more commonly in the form of just Planck's constant. So if you plug in your conversion for h bar to h, and you should pause the video and do this for yourself and see if you end up with the following result. So h squared n squared over 8ma squared. Oh, I lost an a over here. That's what I was missing. Phew. Okay. Now they should match up. All right. So here are the energy levels for a particle in a box. Okay. So one thing to note about our energy levels is that we have a bunch of constants here, right? So remember just Planck's constant, mass of our particle, A represents the length of our box, and then we have popping in to our expression that integer n, which tells us that our energy levels for a particle in a box are in fact quantized. Okay, so that, remember, is in distinct contrast to what would be predicted classically, right? Remember, classically, we can have any value of energy on our continuum, okay? Here, by solving the Schrodinger equation for the particle in a box, we naturally get those quantum numbers arising in our expressions for the energy, okay? We get that quantization of energy arising naturally from solving the Schrodinger equation. So if we think back to our Bohr model, right, where Bohr came up with this equation that worked by just including this quantization idea, okay, now we have arrived at that quantization idea naturally by using all of the principles that go into solving our Schrodinger equation. So it's a much more kind of coherent and satisfying arrival to our quantization result. And more specifically, we see that those integers, the quantization of our energy, arises essentially from the fact that we have applied our boundary conditions. Okay, so the fact that we have a localized particle, so our n, remember, popped up here when we were applying our boundary conditions. So our quantization basically is a result of localizing our particle. If we had no bounds to our particle, if we allowed our particle to run free over all of space, over infinite space, then we would never get the quantization result. Okay, so let's look a little bit closer at our energy levels for the particle in a box problem. So we have our energy expression, our quantized energy levels for the particle in a box. Okay, so the first thing we want to think about is what's our minimum energy level? What's our ground state energy? Okay, so classically, remember, we could occupy 0, right, as our lowest energy state for a particle. All right, is 0 the lowest energy that our quantum mechanical particle can occupy? Well, let's remind ourselves of our limits on our integer n, right? So remember we said that n starts at 1 and can go on to infinity. Currently we don't have any upper bounds on our integer n, but we do have a lower bound, right? So remember we said that n can't equal 0 for this particular problem because then that would result in not having a wave function, which is not an interesting problem because that means we don't have a particle. Okay, so n equals 1 is our lowest energy level, so let's calculate our ground state energy. Okay, so if we plug in 1 for our n, we get h squared over 8ma squared. Okay, so one thing that jumps out at us is that this is not equal to 0. Okay, so we are again not matching with the classical picture. Okay, so classically we could have 0 as our minimum energy. Quantum mechanically we have a non-zero value for our minimum energy. So if we want to draw that on our energy level diagram, our energy level for n equals 1 would be somewhere h squared over 8ma squared above 0. Now we'd have to plug in our length of our box and mass of our particle, but we know that it's not going to be 0. Okay, so one thing to notice here is that there's a special name for this minimum energy that you will see pop up when we look at these quantum mechanical systems, and we call this the 0 point energy. Okay, so here's a term that you want to become familiar with. The 0 point energy is essentially just the minimum energy level. So sometimes, depending on the system, that minimum energy level will be for n equals 1. Sometimes we'll be able to occupy an n equals 0 state. Okay, so it's going to depend on how you set up your problem. But the lowest energy level is what we will refer to as a 0 point energy. Okay, and we will shorthand that as ZPE. Okay, so n equals 1 here. That's our 0 point energy for our quantum mechanical particle in a box. Okay, so Then we could write our higher energy levels on this diagram. So we see that we scale by n squared. So hopefully you can recognize that our lines are going to get further and further spaced apart as we go to higher and higher energies. So we can sketch those on there. So I'll just do a few. And these are obviously not to scale, but hopefully you get the idea that our energy levels become more widely spaced as our energy levels increase, which is opposite of what we had for the Bohr model, where our energy levels became closer and closer spaced due to that 1 over n squared dependence. Okay, so we have kind of the opposite situation happening with our energy levels than we did for the hydrogen atom. Okay, so one thing I want you to do at this point is to see if you can picture how your energy level spacings, how your delta E's for these different excited states will change as you change different factors on in your energy equation. So how will the energy spacing change as you change the dimensions of your box? Okay, so what happens if your box gets larger or smaller? How are those energy spacings going to change? Okay, you should notice that the more you confine your particle, right, you'll see a certain kind of trend happening there. Okay, so I will leave that to you to explore a little bit with. But for now, we'll call that good with our particle in a box problem. So hopefully that was helpful in walking you through that first solution of our Schrodinger equation to a pretty simple problem. But hopefully you saw that we were able to obtain wave functions and our energy eigenvalues for that problem. And we will do some more work with this in class and in lab, so you'll get a few more opportunities to play around with these ideas. Okay, thanks.